Air temperatures on Earth have been rising since the Industrial Revolution. While natural variability plays some part, the preponderance of evidence indicates that human activities, particularly emissions of heat-trapping greenhouse gases, are making our planet warmer. The maps above show temperature anomalies in 5-year increments since 1880, based on an ongoing temperature analysis led by scientists at NASA's Goddard Institute for Space Studies, GISS. These are not absolute temperatures. Rather, they show changes from the norm. The data reflect how much warmer or cooler each region was compared to a base period of 1951 to 1980. The global mean surface air temperature for that period was 14 degrees Celsius, 57 degrees Fahrenheit, with an uncertainty of several tenths of a degree. The image below shows global temperature anomalies in 2025. According to NASA scientists, the planet's average temperature that year was 1.19 degrees Celsius, 2.14 degrees Fahrenheit, above the 1951 to 1980 average. At the time, 2024 remained the hottest year since record-keeping began in 1880. As the maps show, global warming does not mean temperatures rise everywhere at every time by the same rate. Temperatures might rise 5 degrees in one region and drop 2 degrees in another. For instance, exceptionally cold winters in one place might be balanced by extremely warm winters in another part of the world. Generally, warming is greater over land than over the oceans because water is slower to absorb and release heat, thermal inertia. Warming may also differ substantially within specific landmasses and ocean basins. In the animation at the top of the page and in the bar chart below, the years from 1880 to 1939 tend to be cooler, then level off by the 1950s. Decades within the base period, 1951 to 1980, do not appear particularly warm or cold because they are the standard against which other years are measured. The levelling off of temperatures in the middle of the 20th century can be explained by natural variability and by the cooling effects of aerosols generated by factories, power plants, and motor vehicles in the years of rapid economic growth after World War II. Fossil fuel use also increased after the war, 5% per year, boosting greenhouse gases. Cooling from aerosol pollution happened rapidly. In contrast, greenhouse gases accumulated slowly, but they remain in the atmosphere for a much longer time. According to former GISS director James Hansen, the strong warming trend of the past 4 decades likely reflects a shift from balanced aerosol and greenhouse gas effects on the atmosphere to a predominance of greenhouse gas effects after aerosols were curbed by pollution controls. Why should we care about 1 or 2 degrees of global warming? After all, temperatures fluctuate by many degrees every day where we live. The temperatures we experience locally and in short periods can fluctuate significantly due to predictable, cyclical events, night and day, summer and winter, and hard-to-predict wind and precipitation patterns. But the global temperature mainly depends on how much energy the planet receives from the sun and how much it radiates back into space. The energy coming from the sun fluctuates very little by year, while the amount of energy radiated by Earth is closely tied to the chemical composition of the atmosphere, particularly the amount of heat-trapping greenhouse gases. A 1-degree global change is significant because it takes a vast amount of heat to warm all of the oceans, the atmosphere, and the land masses by that much. In the past, a 1 to 2 degree drop was all it took to plunge Earth into the Little Ice Age. A 5-degree drop was enough to bury a large part of North America under a towering mass of ice 20,000 years ago. Global temperature records start around 1880 because observations did not sufficiently cover enough of the planet prior to that time. The line plot above shows yearly temperature anomalies from 1880 to 2020 as recorded by NASA, NOAA, the Berkeley Earth Research Group, the Met Office Hadley Centre, United Kingdom, and the Cowton and Way analysis. Though there are minor variations from year to year, all 5 records show peaks and valleys in sync with each other. All show rapid warming in the past few decades, and all show the last decade as the warmest. The NASA GISS team chose the period of 1951 to 1980 as its baseline, largely because the US National Weather Service uses a 3-decade period to define normal or average temperature. The GSS temperature analysis effort also began around 1980, so the most recent 30-year period was 1951 to 1980. Their objective is to provide an estimate of temperature change that could be compared with predictions of global climate change in response to atmospheric carbon dioxide, aerosols, and changes in solar activity. NASA's temperature analyses incorporate surface temperature measurements from more than 20,000 weather stations, ship and buoy-based observations of sea surface temperatures, and temperature measurements from Antarctic research stations. These in situ measurements are analysed using an algorithm that considers the varied spacing of temperature stations around the globe and urban heat island effects.
Images, Hansen J. and others. 20%.
Hansen J. and others, 2010. Global surface temperature change. Reviews of geophysics, 48. NASA, 2026, January 14th. NASA releases global temperature data. Accessed January 14th, 2026. NASA, 2025, April 3rd, GIS surface temperature analysis. Frequently asked questions. Accessed January 14th, 2026. NASA Earth Observatory, 2024, November 19th, charting the exceptional unexpected heat of 2023 and 2024. Accessed January 14th, 2026. NASA Earth Observatory, 2015, January 21st, why so many global temperature records? Accessed January 14th, 2026. NASA Earth Observatory, 2010, June 3rd, global warming. Accessed January 14th, 2026. NASA Goddard Institute for Space Studies, 2025, December 1st, GIS Surface Temperature Analysis, GISTEMP. Accessed January 14th, 2026. Keep exploring.